Get this started. Welcome to the galvanizing webinar. The title of the webinar today is Computational Modeling and Field Validation, of Advanced Thermal System for Energy, Carbon, and NOx Reduction. Before we start the webinar, I would like to go through some important reminders for the attendees. With that, let me start my presentation. Please note that the attendee audio is disabled. Questions to the presenters should be done through the Q&A feature, which if you roll your mouse to the bottom of the screen, will show it. Please avoid sending any questions in the chat box. If you do send them through the chat, we will ask you to resend them through the Q&A. This way we can keep track of all the questions. The questions will be answered at the end of the webinar. Please note that this session will be recorded and it will be available on demand replay at AIST's websites. Any photos and recordings of the presentations is prohibited. If you have any technical difficulties, contact us at training@aist.org. As with all our events, the AIST antitrust guidelines are in front of you. They emphasize the antitrust law that prohibits agreements between individuals to regulate prices or to hinder or limit a competitor. We also have antitrust or anti-harassment policy, which emphasizes the importance to provide a harassment-free environment regardless of age, race, disability, gender, or gender identity. I'd like to introduce our sponsors, POSCO and Saint-Gobain. Saint-Gobain Performance Ceramics and Refractory Designs develops and supplies solutions and services for extreme operating industrial conditions. Their engineered ceramics and refractory products are manufactured to the highest industrial standards and deliver enhanced performance while minimizing environmental impact. And POSCO is the sixth largest steel company in the world, and they supply over 10 million automobile steel products worldwide. Next, I'd like to introduce our moderator, Nikhil Kulkarni. Nikhil completed his bachelor's degree in metallurgy and his master's in material science and engineering from the University of North Texas. He then started working as a process metallurgist at Steel Dynamics in Columbus, Mississippi, with primary focus on hot dipped galvanized and galvalume coated products. Nikhil currently works as the product metallurgist at SDI's Butler division in Jeffersonville, Indiana. Nikhil is our chair of the AIST Galvanizing Technology Committee, and he also serves as the board of director for the Zinc Aluminum Coaters Association. Nikhil, I'll pass it off to you.
Thanks a lot, Ken, for the lovely introduction, and greetings, everyone. I have the honor to introduce all the presenters over here. I'll start with Mr. Tom Brizelden. Tom is the Global Director of New Business for Saint-Gobain's Performance Ceramics and Refractories Group. He works with the largest steel producers in the world to help reduce energy and emissions using advanced thermal ceramics, computational modeling, and additive manufactured advanced silicon carbide. Mr. Brizelden taught heat transfer, thermodynamics, and fluid mechanics at Penn State University for 10 years. Concurrently, he started a spin-off company, Spinworks, that to date supplied energy savings components to the steel industry with a cumulative 2 trillion BTU per year impact and equivalent 117,000 tons of carbon dioxide. Spinworks was acquired by Saint-Gobain in 2017 and is continuing to accelerate the adoption of energy and emissions reducing technology for thermal manufacturing processes. Next, please. Can you go move on to the next presenter? Okay. Dr. Bradley Nakanishi has been with Saint-Gobain for 3 years. He manages R&D activities for total burner solutions and supports deployment of TBS technologies to new and existing process heating applications. He holds a PhD in materials science and engineering from Massachusetts Institute of Technology. Moving on to Mr. Yunsik Jiang from POSCO. Yunsik Jiang received a bachelor's and master's degree in mechanical engineering and has been working with POSCO for 17 years since 2004. He was dispatched to World Steel in Brussels for 1.5 years to establish CO2 data collection system. He has served as team leader since 2017. Yunsik has been a customer for Saint-Gobain for total burner solutions and other refractory solutions. I welcome all the presenters and thank you for imparting this knowledge to all our attendees over here. And moving on, I think I'll hand it over to Mr. Brizelton, if I'm right. And guys, all the attendees, one more thing, as I'm reiterating what Ken said, if you have any questions, please type in the Q&A dialog box, which is on the bottom of the screen. If you can scroll down, you can see that. And type it there only, not in the chat session. Thank you very much.
Thank you, Nikhil. And thank you, Ken, for the introduction today. And thank you, everyone, for attending today's webinar on computational modeling and field validation of advanced thermal systems for energy, carbon, and NOx reduction. Our focus today is on enhancing radiant tube combustion systems in continuous galvanizing and annealing lines, where we are interested in reducing fuel, carbon, and NOx to help companies meet their near-term 2030 and long-term 2050 sustainability goals. To help foster near-term implementation with excellent ROIs, solutions will be discussed that are retrofit in nature and require a total solution, including advanced thermal designs, computational modeling, and testing. A further goal is that these designs have minimal impact on the burner and control system. I will discuss shortly additive manufacturing of twisted tapes, twisted channels, and flame splitting inserts that meet the goals earlier stated. Brad will show you how these are optimized using computational modeling and testing. Yunsik will discuss both laboratory and field validations of the proposed systems. While the focus today is on radiant tube combustion systems, the method is applicable to direct fired burners as well. While radiant tubes are small when compared to something like blast furnace or EAFs, both individually and when combined, their impact on energy, carbon, and NOx generation can be significant. A single radiant tube will typically use 3 million cubic feet of natural gas a year, generate 150 metric tons of carbon, and 565 pounds of NOx. If we apply a total solution to this that reduces energy by 20% and NOx by 15%, the impact is impressive when applied to 100,000 radiant tubes and will go a long way to meeting the world's environmental goals. 1.6 billion cubic feet of natural gas, 3 megatons of carbon, and 9 kilotons of NOx can be achieved through adopting relatively simple but innovative concepts. So let's dive in. The enabling material platform that pretty much makes everything possible is the ability to additively manufacture advanced silicon carbide. This includes both traditional 3D printing of complex shapes and the use of unique powder extrusions to make large format designs for industrial applications. In some cases, this material will be joined to more traditional materials such as reaction bonded silicon carbide and alpha bonded silicon carbide. In order to achieve energy, carbon, and NOx reduction goals, the material plays a critical role in allowing these designs to operate effectively in extreme environments, namely high temperature to meet all applications, thin walls, high thermal conductivity, and emissivity for excellent heat transfer. A non-porous, low oxidation material matrix is required. These elements combine to help reduce thermal shock, resulting in a perfect material for long-term life in a combustion environment, both in natural gas and coke oven gas applications. "3D printing allows us to move to advanced thermal designs that cannot be made with traditional methods of slip casting, pressed, extruded, or even injection molded designs. We can do enhanced channels, tapes, fins, nozzles, and a variety of different tubes with very complex features." So let's zero in on the radiant tube itself. We want uniform heat transfer from the tube to the steel. Minimum energy use, CO, CO2, and NOx generation. Preferably less than a 2-year return on investment or payback. In a report generated by the Department of Energy, they identified the theoretical practical reduction of energy as going from 1 million BTUs per ton to 0.65. This corresponds to a CO2 reduction per ton from 117 to 76 pounds. And then the South Coast Air Quality Management District, which seems to be the most stringent in the US, is targeting less than 40 ppm for industrial applications in industrial heating processes. So with all of this in mind, we want to emphasize the radiant tube. We want to enhance the radiant tube heat transfer, improve the heat exchanger effectiveness, and simultaneously reduce NOx. While this sounds trivial, several of these statements can be contradictory. As an example, increased efficiency can require higher levels of preheat air, which, if not managed properly, can increase NOx. The unique issue enhancing the radiant tube heat transfer is that the burner leg utilizes both convection and radiation heat transfer from the flame. When the combustion process is complete, in the third and fourth legs, the exhaust gas loses nearly all of its radiative properties. Thus, convection is the primary means of heat transfer and is lower than that of the combined. So how do we make the exhaust leg look like a burner leg? The use of a spiral twisted tape insert provides an effective means when combined with additive manufacturing to make a device that absorbs exhaust energy and re-radiates similar to a flame. Interestingly, we find that a ratio of the surface area of the tube to that of the twisted tape being approximately 1 gives the ideal balance of radiation and convection in the exhaust leg. Additive manufacturing, as compared to slip casting or injection molding, allows the twist rate to be easily modified and optimized for a given radiant tube. While increasing the twist rate further enhances the heat transfer, overheating may occur. However, this may be an advantage in, for example, a radiant tube made of ceramic. Here's a quick visual demonstration. Here's a quick visual demonstration of twisted tape inside a radiant tube. Let's move this over here. Typically, 3 to 18% energy and CO2 reductions occur with minimal pressure drop. So how do we enhance the recuperator? The effectiveness of the heat exchanger recuperator is driven by the overall heat transfer coefficient and surface area. The temperature tends to be fixed by the application. Recuperators are designed as simple straight tubes or enhanced with fins and bumps. With this type of design, In a parallel flow heat exchange design, overall system efficiencies are typically 60 to as much as 68%. Enhancing this design needs to address both improvements to the surface area and heat transfer coefficient in order to minimize pressure drop in the system. Extending the concept of a twisted tape to that of a heat exchanger, a twisted channel is shown to be an effective means of increasing both surface area and overall heat transfer coefficient simultaneously. The twisted channel imparts a velocity vector perpendicular to the heat transfer surface that acts as jet impingement. This increases the Nusselt number and the overall heat transfer coefficient by 25% at the mid-range of the design flow. Increasing the surface area with the assistance of additive manufacturing allows for a significant change in surface area as compared to fins and bumps. A typical tube recuperator will have a surface area of 450 square inches. A shallow twist 3-fin design can match this surface area. However, when increasing both the number of twisted channels and twist rates, a surface area of 2 times is achieved. The corresponding improvement in heat transfer coefficient allows overall radiant tube efficiencies to approach 85%. Thus, 5 to 30% energy and carbon reductions can be realized. The combined reduction of flow rate and improved heat transfer coefficient and counterflow design allow pressure drops to be minimized in the overall system. This gives an example of how energy savings is impacted as we increase twist rate and thus the surface area of the heat exchanger. And then also the changes in combustion air preheat as a function of the twist rate of the heat exchanger. Initially, internal exhaust gas recirculation was explored as an effective means of reducing NOx. While a reduction in the range of 35 to 50% was achieved, it was limited to a few burners or required modifications to existing burners. Here is a visual demonstration of the concept. So here we have a nozzle, combustion occurring inside the device, and then recirculating the exhaust gas to help reduce NOx. Due to the impact on the burner and control system, a computational evaluation along with laboratory validation identified an effective means of NOx reduction with minimal impact on the burner or control system. Flame splitting is showing the ability to reduce NOx by up to 70% in a variety of existing burners. This includes nozzle mix, partial premix, air or gas stage combustion, and low NOx burners with and without exhaust gas recirculation. Brad will now further expand on this concept and the optimization of total sustainable solutions that combine improved radiant tube heat transfer and twisted tapes, spiral core inserts, increased heat exchanger effectiveness, and NOx reducing flame splitting devices.
All right. Thank you, Tom. Hello, everyone. Thank you for joining us for this exciting discussion. We encourage you to please share questions with us in the Q&A. My section will be in 2 parts. First, I'll review benefits and challenges for improving combustion heating efficiency and emissions. Then, I'll show how we can realize this using the POSCO-Saint-Gobain collaboration as a case study. Improving heating efficiency helps to reduce energy consumption or increase product throughput, or some combination of the two depending on operating conditions. To illustrate this, consider the 3 Sankey diagrams shown here, illustrating the energy flows in a recuperated furnace. These diagrams could represent a continuous annealing line utilizing radiant tube heating, or any indirectly or directly fired heating process with recuperation. The left diagram is for a conventional metal plug recuperated system. Here, energy inputs that is the fuel, air, and their mutual combustion heat, are 100 arbitrary energy units. You can also see the heat flowing to the load, that is the steel strip, the exhaust, and furnace leaks. The right diagrams show two extremes for the same system, now utilizing high efficiency ceramic inserts and recuperators. The top furnace operates at similar throughput to the system on the left, but here 18% energy savings are obtained. Similarly, the bottom furnace operates at the same energy input while adding 22% throughput. Real systems likely operate with some combination of the two. We'll focus on energy savings in this talk, but the key point here is that energy savings and throughput are related benefits of higher heating efficiency. And in terms of specific CO2 emissions, measured as CO2 per ton of steel, for example, any combination with the higher efficiency system reduces specific CO2 emissions. In this example, both give 18% reduction. The two main challenges for improving efficiency of recuperated combustion heating systems are pressure and NOx. Here, I schematically show how pressure, that is the pressure drop between the air blower and exhaust, recuperator surface area, NOx emissions, and preheat air temperature vary with energy savings. Focusing on the left, you see how recuperator surface area and pressure both increase as energy savings increases. Typical blowers operate at low pressure, and system upgrades add additional costs. Fortunately, twisted channel recuperators may be optimized using computational modeling to minimize pressure drop and avoid blower upgrades while providing energy savings. Looking on the right, reducing energy use by recuperation increases the preheated combustion air temperature as more heat is transferred from the exhaust to the combustion air. Because NOx is a thermally activated process, you may find significant increases in NOx at higher flame temperatures while targeting additional energy savings. Fortunately, this may be avoided by utilizing ceramic inserts to reduce NOx by up to 50%. To illustrate the benefits and challenges in action, I'll share how Saint-Gobain assisted POSCO with reducing energy use by 24% and NOx emissions by 15% in a field installation. In the interest of time, I'm not going to share many details here, but please, I encourage you to post any of your questions to Q&A. The left bar plots summarize results from a series of trials at POSCO and RIST, a research affiliate of POSCO. The baseline system consisted of a W-tube, an air-staged burner, an EGR or external gas recirculation system, and metal plug recuperator. The other trials utilized various configurations of total burn solutions, which includes heat core, NOx buster, and Spirocore. Leveraging Saint-Gobain's pilot test furnace and extensive experience with heat core and Spirocore, designs may be optimized with testing and modeling to achieve the target performance. Notice in trial A, with heat core version 1, without a NOx buster, 16% energy savings are obtained, while NOx increases by 44%. This is a direct result of the higher combustion air preheating with heat core. To combat higher NOx, NOx buster, a ceramic insert, may be positioned downstream from the burner in the flame, reducing both peak temperatures and NOx, as the figures on the right illustrate. After just a few iterations of testing at RIST with modeling input from Saint-Gobain, we created a NOx buster that reduces NOx below POSCO's targets while providing significant energy savings. Finally, I'd like to highlight how we solved a critical problem that we encountered during the field trials involving soot. Shortly after POSCO restarted their furnace installed now with total burner solutions in a single zone, they observed strange behavior requiring zone shutdown and further investigation. After removing the burners, they discovered significant soot deposits on the NOx busters in multiple radiant tubes from the zone. Not a great situation. Long story short, Saint-Gobain's R&D teams reproduced POSCO's conditions using our own pilot furnace based in Paris and conducted a series of tests and simulations to determine the root cause and develop a viable solution. Together, POSCO and Saint-Gobain learned that managing NOx buster position during the installation process is very important to prevent soot formation, and we obtained a good solution that ultimately simplified the installation process and had little to no impact on furnace operations. To sum up, I hope, you take away a better understanding of the benefits and challenges for reducing energy and carbon from combustion heating, and how testing and modeling can be used to deliver significant improvements to industrial processes. I look forward to answering your questions in the Q&A. It's my pleasure now to hand off the presentation to Yunsik, who will provide more details about POSCO's solution. And thank you for your attention.
Excuse me, Yunsik, you're muted.
Muted.
Sorry. Good morning, everyone. My name is Yunsik Jung. I am working as team leader of energy department in POSCO, which is Korean steel company. I am in charge of developing innovative technology to save energy and reduce CO2 emissions. I am pleased with having a presentation on laboratory and field validation for energy, carbon, and NOx reductions. Saint-Gobain and POSCO have been cooperating on this project since 2018. As you know, energy price is increasingly tremendously, especially natural gas. Huang Steelworks consumes approximately 100 million US dollars of natural gas for fuel in reheating furnace and annealing furnaces, etc. Energy saving of natural gas is essential not only to save energy costs, but also to reduce CO2 emissions. Silicon steel plant in Huang Steelworks has 495 radiant tube burners using 82 million normal cubic meter of the natural gas. Its furnace temperature is 950 to 1050 Celsius degree, which is the highest and the most severe temperature conditions in terms of applying innovative technology. We choose the most severe conditions for experimental and field circumstance to prove energy savings and its robustness. I will explain how to install and test. In order to perform laboratory validation, we decided to proceed in two steps. Step 1, spiral core is installed in fourth leg of the radiant tube line. Step 2, the existing recuperator is replaced with a heat core, and NOx booster is installed in the first straight leg of the legend tube. Refer to the graph 1, spark core produced an increase in temperature of the legend tube. Refer to the graph 2. When taking a close look at the first leg of temperature, a 25 Celsius degree increase observed. And you can see that heat core used a counterflow design to obtain maximum temperature differential and heat transfer. I will explain its detail on the next slide. Legend tube insert, so-called spiral core, are twisted tape inserts. They bring 5% fuel saving. Lab maximum furnace temperature was just set up to 900 Celsius degree due to limited lab circumstance. It has 6 elements, but field test was performed by actual furnace temperature. I will explain this result later. During the lab test, feasibility study and energy saving effect were verified. We can optimize combustion air ratio 1.1 to 1.2 typically. 2 types of inserts were examined. As a result, Saint-Gobain products was selected according to the better energy saving effect. In addition, CFD analysis of legend tube was performed as the following features. As you told you, we found its energy saving effect is 5%. Step 2 is about the new recuperator, which is manufactured by 3D printing technology. Its application is way more difficult for us. However, its energy saving effect is 11.5%. For this product, 2 companies had long discussions and signed an NDA. Saint-Gobain provided 3D printing recuperator and NOx booster and cooperate with lab and field test, and their experts were dispatched to Korea to support our experiment. POSCO supervised lab and field tests and give advice to redesign 3D printing recuperator and NOx booster. The new designed recuperator has much more heat exchange surface area compared with previous version recuperator. Fin-type heat exchanger has 0.4 meter square heat exchange area. The new one has 2.7 meter square heat exchange area. In addition, NOx booster is installed and tested to reduce NOx emissions due to the preheated temperature increase. I will summarize overall test result. RTI and the new recuperator bring 16.5% fuel saving, respectively 5% and 11.5%. And its NOx emissions also 17.2% reduced from 134 ppm to 111 ppm. You can find this in the table. All detailed data to explain its energy saving effect and NOx reductions. As a result, combustion air temperature is also increased plus 84.7 Celsius degrees. I will explain field validation briefly. POSCO invested RTI 68 sets and energy saving effect is 7.9%. Each zone has different furnace temperature and heat load. We decided to install 4 and 5 elements of RTI respectively, according to the zone heat load. For lab test, we used 6 elements of RTI. The new recuperator 10 sets were installed in the same annealing furnace. Its remarkable energy saving effect is 15.3%. Our team also was surprised. You can see the graphs show that energy usage of the 5 zone is dramatically reduced. In conclusion, lab test result is 16.5% and field test is 23.2% in terms of energy saving. Especially RTI's 68 sets are installed in all zones except 1 and 8 zone, and it runs successfully without any troubles. And we will have confidence the new designed recuperator energy saving effect. In 2022, POSCO will invest 58 sets of the recuperator and NOx booster in the same annealing furnace. Furthermore, NOx booster 13 sets are installed to another annealing furnace to reduce NOx emissions. And also, 50 sets will be purchased and installed. NOx booster reduces more than 50% NOx emissions. And also, we launched a new R&D project for continuous annealing line with Liszt and Saint-Gobain. This project will enable us to lead energy initiative, not only energy saving, but also reduce CO2 and NOx emissions. It will also focus on the use of the both natural gas and coke oven gas. I'm going to wrap up this presentation referring President John F. Kennedy's speech, because what we did and are going to do is just like go to the moon. We choose go to the moon. We choose go to the moon in this decade and do other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best our energies and skills. Because that challenge is the one that we are willing to accept, when we are unwilling to postpone, and when we intend to win, and the others too. Thank you for your attention. If you have any questions, feel free to ask me. Thanks.
Thank you, Yunsek, and thank you, Tom, and thank you, Bradley, for your presentations. Okay, now I'll go ahead and read out the questions, and any of you guys who wants to answer can go ahead and answer. The first one is, how does modeling affect the qualification times, and what resources does Saint-Gobain have to support modeling?
Yeah, so
that sounds like a good question for you.
Yeah, to say maybe I could take that one. So yeah, modeling efforts, depending on their complexity and scope, they could be a few hours or a day or two, or up to several months. But I guess I like to think that by taking the time to do some of the studying up front with modeling, that we can kind of reduce a lot of the pain and really get to the good solution quickly when we go to do the installation at customer sites. In terms of the resources, We have two teams. One's based in North America, one's based in Paris at our R&D centers that can support on computational fluid flow modeling. Our team based in Paris, they're also very much experts on combustion modeling. I don't know if you may know, but Saint-Gobain, we also have a significant portion of our business dedicated towards glass production and glass melting. So for that application, combustion's very, very important. And we have experts that are knowledgeable in both glass melting as well as steel heating.
Thank you. We'll go on to the next question. What is the typical lifetime of twist spiral device? What is the usual failure mode?
I think I can answer that question. I'll start with the second. What is the usual failure mode? So the usual failure mode of the spiral core is where the tube life. So, radiant tube will last maybe 3 to 5 years, sometimes a little bit longer. A lot of times, as the radiant tube fails, it can capture the spiral core in the tube. Some customers will remove the spiral core before that happens, and we've seen 2 to 3 tube changes. So, pick your number, greater than 10-year life on the spiral core system.
Thank you. You use the NOx buster to decrease NOx emissions of existing burners. Are the technologies usable for pull systems or just for push-pull? Can the technology be applied to burners of other manufacturers?
I think I can answer that question also. So the NOx buster can be applied in push-pull, and pull systems. The pressure drop is very low on the NOx buster. I would say 4 years ago, it was limited to 1 or 2 burners. Today, because of the resources of the computational modeling and the testing that Brad discussed in Paris, we're finding that it's applicable to a variety of different manufactured burners. To date, we've tested it on at least 5 or 6 different burners with very, very similar results. And those were, like I said, nozzle mix, partial premix, both air stage and gas staged combustion, as well as low NOx burners. And it was used both with exhaust gas recirculation and without.
Thank you. POSCO test. Do you have data about the difference in the final exhaust temperature before and after increase of efficiency?
I have data, but I can't remember the exact figures, but I'm sure that the final exhausted gas temperature is decreased because of the preheated air temperature is increased. So I will answer these questions later.
Okay. What is the final NOx performance of this solution? ppm at 3% oxygen or mg Newton meter cube at 3% oxygen?
I think I can answer that question. So, on the one trial that was discussed today, the NOx level with the heat cores increased over 200. I think it was close to 250 ppm, and the NOx buster brought that down to 113 ppm. And this is at 3% oxygen corrected. We also have other cases, where recuperation wasn't used, and we've gone from in the range of 900 to 100 ppm at 3% oxygen down to between 30 and 40 ppm of NOx at 3% oxygen.
What is the LHV efficiency of this solution?
Brad, maybe you have that number, but we typically approach, depending on what the customer's needs are, what the NOx levels, we can approach 85%. I would say typically we're in the high 70s to low 80%.
Yeah, I was gonna say I'm seeing some of the trials that we showed you from POSCO were in the range of like 77 to 81% LHV.
Okay. Can you provide a better explanation for soot in Knox Buster and how it was solved?
Sure. Maybe I'll share my screen to go back through that. So yeah, one of the problems we encountered during the installation was that we found that the Knox Buster positioning was installed kind of in a variable arrangement, and so we did some additional testing at SGR Paris, where we took a similar size radiant tube and burner setup and operating conditions. We placed the Knox Buster in the radiant tube and took a look at different positioning effects of kind of the burner, the air fuel ratio, and other conditions of the application to try to identify what might have been causing the soot formation that we observed during the field trial. And basically what we ultimately found was that the positioning is very critical, as well as the excess oxygen or air fuel ratio. It's for formation of NOx here. And we identified one position here labeled as position 3, where for a very wide range of air fuel ratios, where POSCO might be operating, that we can completely eliminate the soot that's formed. I guess I should mention, during this trial, what's really nice is, in our pilot or lab scale furnace was that, we were able to reproduce the kind of effects of soot formation on the Knox Buster that are pretty similar to, I think, what POSCO had observed during their field trial installation. You see some of those images of the soot inside of the Knox Buster here.
Okay. All right. Next question. Is this RTI spiral tapes, Knox Busters only in silicon carbide tubes, or it can also be used with metallic tubes?
I would say 95, probably even 98% of the applications have been in metallic tubes. Very few applications in ceramic tubes. Currently, there are very few ceramic U tubes out there, or W tubes. The heat core technology is applied in single-ended radiant tubes that use ceramic, but really to date it's been metallic tubes.
Thank you. Next one. What is the energy consumption and NOx related to making the recuperator and Knox Buster? Is it possible that the energy savings in a steel plant in the big picture is just energy reallocated to this technology's processing? Relates to scope 3 emission in supply chain, and is the savings of energy emissions in steel plant greater than the energy emissions of processing of this technology? It's a long question, guys.
I think are you going to take a stab at that, Brad?
Yeah, I was going to say. Go ahead. Yeah.
Yeah. So the Knox Buster, in terms of its operation, we're seeing in the last trial we saw an increase in system efficiency, and therefore it doesn't require any additional energy to operate, and therefore we're not taking any additional energy, fan power to make the device operate. And then, as Brad mentioned in his presentation, one of the nice things about the heat core and the Knox Buster and the spiral core is they can be custom designed specific to a pressure requirement of a furnace. I hope that answered the question.
Yeah, and maybe Tom, if I may add that we're currently working on putting together LCA or life cycle analyses for our products at Saint-Gobain. So we'll hope to have an LCA to go along with our product offering here very soon.
All right, thank you. Okay, next question. We have seen the use of these solutions for W-type radiant tubes. Can it also be used for single-ended radiant tubes?
Yeah, so the heat core can be used as a replacement for the recuperator in a single-ended radiant tube. In addition, we have I think maybe people have seen the flame tubes, which tend to be just straight tubes that are combined within the single-ended radiant tube. We can apply a spiral core type device as a replacement for that.
Okay. Do radiant tube deformation affect the generation of soot in the NOx buster?
Maybe
Brad, you want
Tom,
to take that?
Yeah, I think my guess here, we have pretty limited experience on this effect with kind of deformation, say after installation. But just given my kind of understanding of how the NOx buster is working and things, that I think the tube shape or deformation of the tube is going to have kind of like a second or tertiary order effect on, like a lower order effect on soot formation, where like kind of the big factors being, as I highlighted in the presentation, being like position, dimensions, and kind of operating conditions.
Okay. Next question. I think there are like 3 questions from the same person. So, guys, if you want me to ask the 3 at a time and then you want to go ahead and answer, how do you want to do it?
Yeah,
I mean,
we
I
do
can-
one at a time. I don't know.
Okay.
Yeah.
How do you begin collaboration with a customer?
I can answer that. So usually, it's either us contacting a customer or customer contacting us with a specific issue or problem in their plant. Energy savings, carbon reduction, NOx. It could be some temperature applications. And then, as you saw with POSCO, it was a full in-depth collaboration, both with their energy efficiency team as well as an external party to do the testing. And so that was a broad scale. We went through laboratory testing, field testing, and that was just with the spiral core. And then we went back into heat core, NOx buster testing in the laboratory, and then into the field. And so, depending on the complexity of the solution and what the customer is looking for, we can collaborate as a total solution provider, or we can do a total collaborative project.
Okay. The next one, what safety measures do you need to put in place before testing begins?
Maybe Yunsik can answer that, but generally the safety measures are highly driven by the plant. So whatever safety measures are required by the plant in terms of personal protective gear or how the furnace is operated during the installations, it's highly driven by the plant. And then of course we have our own protocol in terms of how to properly handle materials and that sort of thing.
Our lab test has a nitrogen fuzzy system to prevent a fire and explosions. So it is very essential to have such kind of the safety safety system. So we prepared more than 4 hours to keep safety before the test.
Okay. All right. What are the main challenges POSCO saw during the testing?
My main challenge is to every furnace, every recuperator has their own dimensions, their own temperature conditions. So in order to adapt this technology, we need to cooperate supply Saint-Gobain and POSCO. We discussed all the expertise from the plant managers. We discussed more than 2 weeks to adapt this technology. So it is not easy to adapt, just to adapt total burner solution. We should analysis, valid air, combustion air, and exhausted fan, ID fan capability. It is very important to discuss the plant manager to adapt this technology.
Okay. Thank you. With respect to coke oven gas trials at POSCO, is the premise that the coke oven gas is being used to fuel radiant tube lines instead of natural gas? What goals are you targeting?
In Pohang Steelworks, we use natural gas as a fuel for the annealing line, but the Gwangyang Steelworks, they use coke oven gas for the continuous annealing line and CGL line. So we expand our experimental and field evaluation for the Gwangyang Steelworks.
Okay. Which type of radiant tubes are better for long life and good efficiency? W type or I type?
I think I can answer that. I think it's highly application dependent. Depending on the type of furnace that you have. But I think the other thing is probably pick a number. 5 years ago, single-ended radiant tubes were probably more efficient than W tubes. And now with the advent of the combined solution of spiral core, heat core, now they're pretty much on par. So now it becomes more of a furnace size. How many burners do you want to manage? And what the application difficulties are.
Okay. Why radiant tubes are damaged at exhaust portion near recuperator area?
I have a couple answers to that. I've seen the metallic recuperators damaged due to flame impingement. So that would be a result of the flame, not the combustion process not being tuned properly. I've also seen the damage occur in external exhaust gas recirculation systems. And again, that had to do with tuning and allowing fuel to come through the recuperator section and then combust later on. Those are kind of the two main failure modes that I've seen. Generally, again, related to the burners not being properly tuned.
Okay. All right. Can this solution be applied to direct fired burners?
Brad, maybe you want to answer, but the heat core technology, as a recuperator, can be applied to direct fired furnaces, probably more as a self-recuperative type application. The NOx buster, we continue to expand the application of that technology. Like I said, originally it was a single burner. Now it's moved to multiple burners as well as direct fired burners. And so it's really showing itself to be an effective technology.
Thank you. How can we learn more about these products?
Tom?
I think the easy answer is, tell everybody about this webinar and then download the webinar presentation so you'll learn about that. Depending on what region you're in, you can contact a Saint-Gobain application engineer. We're pretty much worldwide. So there are application engineers throughout the world that you can begin initial discussions about, and everybody is trained in the total solutions.
Yeah, I'd say maybe add just, please check out our website or feel free to reach out to us at Saint-Gobain.
Right. At what temperature will the NOx buster deform?
Right around 1450, maybe 1500 degrees Celsius.
All right, final question. Is there any alarm system to identify the damages in recuperator or radiant tube in advance?
Brad, maybe you want to answer that. I think the answer to date is no, but Brad might want to expand on that with some some new
Yeah,
direction.
yeah, I think, yeah, today we don't really have that kind of in situ type of detection technology, but I think this is a really kind of interesting question and definitely something that we've thought about working towards. So, if for sure, if it's something that you're excited about or interested in taking a look at, we'd be happy to talk maybe more offline about this.
All right. I think we've done answering all the questions, and we're also pretty good on timing wise. Great job, guys. For Yunsik, Thomas, and Bradley on answering all the questions and also for the great presentation. I'll hand it over to AIST for if they have any finishing comments. And thank you all the attendees for attending this great seminar. Thank you.
Thank you very much. Thank you.
very much.
Yeah, thank you.
Sorry, Nikhil, didn't mean to stomp on you there for a second. All right, bringing that up. Thank you, Nikhil, for moderating this, and thank you each of the presenters and our sponsors, Saint-Gobain and POSCO. Before we conclude, I'd like to review some of the upcoming training that AIST is holding during the spring of 2022. The modern electric furnace steel making is a practical, let me get my video on here, practical training seminar. And that will be the February 7th through the 11th in Orlando with a tour of Nucor Steel, Florida. Long Products Rolling Seminar will be the 21st through the 24th of February in Atlanta with a tour of Cartersville. The Energy and Utilities, a roadmap to energy efficiency, sustainability, and carbonized steel industry will be the 14th through the 17th of March in Knoxville with a tour of the Oak Ridge National Laboratory. Digital Transformation Forum for the steel industry is 14th through the 16th of March in Indianapolis. Sheet Processing and Finishing Lines, a practical training seminar, will also be in March in Indianapolis, and that will have a tour of SDI's Heartland facility. Then the 28th Crane Symposium will be in June in Milwaukee. Further details can be found at AIST.org at the website shown on that page. Again, thank you for attending to all our attendees, and we look forward to seeing you at our future events. With that, we'll conclude this webinar. Thank you all.
Thank you. Thank you, Ken.
Thank you.
And
Thank you
happy
for-
Thanksgiving.
Thank you,
to all.
Ashley.
Happy Thanksgiving.
Happy Thanksgiving.
Happy Thanksgiving.